Somewhere beneath your feet, right now, something is moving that scientists cannot fully explain. Not an earthquake you would feel, not a volcano you could see coming, something far stranger, buried thousands of kilometers down, in a place no human being has ever visited and no machine has ever reached. For most of human history, we assumed the ground beneath us was simple. Solid rock, then more solid rock, then a molten core, then nothing but heat and pressure all the way to the center. But in the last few years, using tools that listen to the planet, the way a doctor listens to a heartbeat, researchers have found evidence that the deep Earth is alive with structures, currents, and anomalies that do not fit the old picture at all. Continent-sized blobs of unknown material, patches of rock behaving like liquid. Glass. Earthquakes happening in places. Earthquakes are not supposed to happen. And now, a new hypothesis so strange that if it holds up, it could rewrite the story of how life on this planet became possible in the first place. This is the story of what is really happening beneath Earth's crust, and why the deeper scientists look, the less certain they become about what is actually down there. For thousands of years, humans looked at the ground with a mixture of reverence and fear. Ancient Greek myth placed the underworld beneath the surface, a realm ruled by Hades, where the dead crossed rivers of fire and darkness. Norse cosmology imagined Niflheim, a frozen abyss below the roots of the world tree. In Mesopotamian belief, the underworld was a house of dust, entered but never left. Across nearly every culture on Earth, the deep ground was imagined as a hidden kingdom, a place of judgment, punishment, or transformation. These were not scientific claims. They were attempts to explain something humans could feel, but never see. Heat rising from volcanic vents, the ground splitting open during earthquakes, rivers of molten rock bursting from mountains that had been silent for generations. The underworld was myth built on top of a mystery that ancient people had no way to solve. It would take thousands of years and one of the strangest tools ever devised before humanity found a way to actually look inside its own planet. The first real crack in that mystery came not from a grand expedition, but from a single scientist studying earthquake records at a desk. In 1906, an Irish geologist named Richard Oldham noticed something odd in the timing of seismic waves recorded around the world after a distant earthquake. Certain waves arrived later than they should have if the Earth were uniform rock all the way down, as though something deep inside was slowing them or blocking them entirely. Oldham realized the only explanation was a distinct composition from everything above it. A few years later, in 1913, the German seismologist Benno Gutenberg refined the measurement, calculating almost exactly where that boundary between mantle and core sat, a figure that modern instruments have barely had to revise in over a century. Then, in 1936, a Danish seismologist named Inge Lehmann, working with earthquake data at a time when few women were permitted anywhere near the top of the field, noticed faint seismic waves that should not have existed if the core were entirely molten. She proposed that at the very center of that molten core sat something solid, an inner core within the outer one. She was right. 3 scientists, working decades apart with nothing but pen, paper, and the patient study of vibrations traveling through solid rock, had built the basic map of Earth's interior that every geology textbook still uses today. It remains one of the most remarkable feats of deduction in the history of science, and it set the stage for everything that came after, including the discoveries now forcing scientists to redraw that map yet again. That tool is the earthquake itself. When the ground shakes, it sends waves of energy racing through the earth in every direction, the same way a struck bell sends sound through the air. Different materials bend, slow down, or speed up those waves in different ways. Solid rock behaves differently than molten rock. Cold rock behaves differently than hot rock. By placing sensitive instruments called seismometers around the globe and recording exactly how earthquake waves travel from their source to the far side of the planet, scientists in the 20th century built the first real picture of Earth's interior. They discovered the crust, thin and core, despite temperatures hotter than the surface of the sun, held solid by unimaginable pressure. It was a remarkable achievement. It also turned out to be only the beginning of the story, because the deeper researchers studied those seismic waves, the more anomalies they started to find. Small. Inconsistencies that did not fit neatly into the tidy, layered model everyone had settled on. One of the strangest of these anomalies sits nearly 3,000 kilometers down, at the boundary between the mantle and the outer core, in a region seismologists call the D double prime layer. For decades, this thin shell puzzled scientists, because sound waves passing through it sped up in ways that 1,000 kilometers underground before researchers at ETH Zurich found an answer. Under those extreme conditions, solid rock does not simply sit still. It flows slowly and steadily the way glacial ice flows across a mountainside over centuries. As it flows horizontally along the base of the mantle, A mineral called post-perovskite aligns itself in a single consistent direction, like iron filings snapping into formation around a magnet. That alignment is what was speeding up the seismic waves all along. It sounds like a small technical detail. It is not. It means that nearly 3,000 kilometers beneath the ground you are standing on, solid rock is behaving like a slow-motion river, one whose currents help drive time, sinking slowly through the mantle like stones dropped into thick honey before finally settling nearly 3,000 kilometers down. These long-lost plates are not gone. They are still down there, still influencing the deep earth today, warping and twisting the rock around them in ways scientists are only now able to map. It raises an uncomfortable question. If pieces of ocean floor from hundreds of millions of years ago are still shaping the deep planet, what else has survived down there, hidden in plain sight beneath every ocean and continent on Earth? That question becomes even stranger when you look at what else researchers have found lurking near the core. Using a technique called full waveform inversion, a method that extracts far more detail from seismic data than older approaches ever could, scientists, mapping the mantle beneath the Pacific Ocean, identified structures so unusual that headlines called them sunken worlds. These are not small features. They are enormous, continent-sized regions of dense, unusually hot rock, sitting at the very base of the mantle, one beneath Africa and one beneath the Pacific. Seismologists call them large, low-shear velocity provinces, but their nickname among researchers is far more evocative: mantle blobs. Alongside them sit thinner, strange patches called ultra-low velocity zones, described by the scientists who study them as lava puddles clinging to the surface of the core like drops of molten wax. Both features slow seismic waves dramatically, a signature of composition unlike anything else in the mantle. For years, nobody could agree on what these blobs actually were. Remnants of ancient collisions, chemically distinct rock left over from Earth's earliest formation, or something else entirely. In late 2025, a team led by geodynamicist Yoshinori Miyazaki at Rutgers University, working with researchers at Princeton, proposed an explanation that connects these strange structures directly to the deepest question in all of science: why life exists on this planet at all. Billions of years ago, in the earliest chapters of Earth's history, the entire planet was covered by a global ocean of molten rock, a scorching sea of magma left over from the violent process of planetary formation. As that magma ocean cooled, scientists expected the mantle to separate into distinct chemical layers, the same way a cooling mixture of juice settles into a heavier, sugary layer at the bottom and a lighter, watery layer above. But when researchers looked at the actual structure of Earth's mantle today, that clean layering separation, they found irregular continent-sized piles clustered at the base of the planet. Something had disrupted the process, and for a long time, nobody could say what. Miyazaki's team concluded that the missing piece was the core itself. Their modeling suggests that over billions of years, elements like silicon and magnesium slowly leaked out of Earth's molten core and mixed upward into the base of the mantle, contaminating what should have been a clean chemical separation and instead producing the uneven, blob-like structures seismologists detect today. It is a subtle process, unfolding across a timescale almost impossible for a human mind to hold on to, and it remains a hypothesis rather than settled fact. One explanation among competing ideas that researchers are still testing. Not every scientist agrees on what these mantle blobs actually are. For years, one leading explanation held that they are simply piles of ancient oceanic crust, the same sunken tectonic slabs found shaping the flow at the base of the mantle, accumulated into denser clusters after hundreds of millions of years of subduction. Another camp argued they had to be primordial material, chemically distinct rock left over from Earth's formation that never fully mixed into the rest of the mantle. The core leakage hypothesis from Miyazaki's team does not necessarily rule out either idea. It offers a mechanism that could explain why the mantle failed to separate into clean layers in the first place, regardless of exactly which material ended up piling into those continent-sized structures. Resolving the debate will likely take years of further modeling, and possibly new seismic techniques capable of probing the composition of those blobs in finer detail than anything available today. That uncertainty is not a weakness in the science. It is exactly how science at the frontier is supposed to look, several serious hypotheses competing against each other, each accounting for some of the evidence, none yet accounting for all of it. But if it holds up, the implications reach far beyond geology. Those same researchers argue that this ancient core-mantle interaction likely shaped how Earth cooled over billions of years, how its volcanic activity unfolded, and even how its atmosphere evolved into something capable of supporting life. In other words, the very features that make Earth different from a dead, barren rock like the Moon or Mars may trace back to a slow chemical leak between the core and mantle that began before life existed at all. As one of the researchers put it, these structures are not random oddities. They are fingerprints of Earth's earliest history, sitting nearly 1,800 miles beneath our feet, waiting for the tools sensitive enough to finally read them. If that were the only mystery, it would already be extraordinary. But the deep Earth keeps offering up things that should not exist according to the models scientists have relied on for decades. In February of 1979, a small earthquake shook the ground near the town of Randolph, Utah, close to the borders of Idaho and Wyoming. It registered a modest magnitude of 3.8, and nobody on the surface even reported feeling it. But when a young researcher named George Zant examined the seismic recordings, something did not add up. His calculations placed the quake nearly 90 kilometers beneath the surface, deep within the upper mantle, in a region where earthquakes were not supposed to be possible at all. Ordinary earthquakes happen in the brittle crust, where rock can crack and slip. Below that, under crushing heat and pressure, rock is expected to bend and flow rather than snap. An earthquake 90 kilometers down looked on paper like a contradiction. For decades, the finding sat unresolved, filed away as an anomaly nobody could fully confirm or dismiss. It took nearly half a century and a wave of new research into a rare and elusive category of tremor called mantle earthquakes before scientists returned to that old Utah data with better tools. Researchers at Stanford, building a method that could distinguish these deep, mantle-originating quakes from ordinary crustal earthquakes using subtle differences in their seismic signatures, produced the first global map of these events, uncovering hundreds of them clustered in regions like the Himalayas and near the Bering Strait. Applying that same careful analysis to the decades-old Utah recording, researchers at the University of Utah confirmed in the summer of 2026 that the strange 1979 event really did occur, nearly George Zant had calculated all those years earlier, deep in a part of the planet where earthquakes were long assumed to be geologically forbidden. It was a quiet vindication of one scientist's careful, doubted work from decades before, and a signal that the deep Earth still holds seismic behavior that current models cannot fully explain. George Zant spent the following decades building a respected career in geology, eventually joining the faculty at the University of Arizona, but the strange Utah earthquake never fully left him. At the time he first calculated its depth, the tools available could narrow the estimate down, but could not confirm it with the certainty modern methods now provide, and there was no way to rule out the possibility that his instruments, or his math, had simply gotten something wrong. An earthquake 90 kilometers underground contradicted the basic physics of how rock was assumed to behave at that depth. And contradicting basic physics is not something a young researcher does lightly. For nearly half a century, the finding sat as an intriguing but unconfirmed outlier. Cited occasionally, never fully resolved, a small crack in the foundation of mantle seismology that nobody had the tools to either close or widen. It took an entirely new global survey method, built decades later at Stanford specifically to separate the faint signatures of mantle earthquakes from the far more common quakes of the shallow crust, before scientists could return to that old recording with confidence. When they did, the 90-kilometer depth held up exactly as Zant had calculated it in 1979. Science rarely resolves its strangest anomalies quickly. Sometimes it takes one patient researcher's calculation, decades of silence, and an entirely new generation of instruments before the ground finally gives up its answer. If rock down there can fracture in ways scientists thought impossible, what other assumptions about the deep planet might also be wrong? There is a wider mystery hiding behind all of this, one that stretches beyond Earth entirely. Of the 4 rocky worlds in our solar system, only Earth has active plate tectonics, the slow, grinding recycling of crust that drives mountain building, volcanic activity, and the long-term regulation of atmospheric carbon dioxide. Mars, roughly half Earth's size, cooled too quickly to sustain the same internal engine, and its surface has been geologically frozen for billions of years. Venus, similar in size to Earth, appears to lack conventional plate tectonics altogether. Its surface instead resurfaced periodically by catastrophic volcanic upheaval rather than the gradual grinding of separate plates. Earth alone, among its rocky neighbors, kept its internal heat engine running steadily enough, for long enough, to maintain plates that split, apart, collide, and recycle themselves over and over across billions of years. Scientists have long suspected that this ongoing churn, this restless mantle convection, is part of what allowed Earth to maintain a stable climate and a long-lasting atmosphere capable of supporting complex life. If the newest research linking core leakage to the deep mantle's uneven structure holds up, it would mean that same restless churn traces back to a chemical exchange between core and mantle in the earliest hundreds of millions of years of the planet's existence, an exchange that essentially set the terms for everything that followed, long before the first cell ever divided. Surface of the sun, held solid only by the crushing weight of the entire planet above it. For decades, the inner core was treated as the most stable, least mysterious part of Earth's interior, a simple ball of solid metal at the bottom of everything. Recent research has complicated that picture considerably, with evidence that the inner core may not be a uniform solid at all, and studies proposing that it exists in what scientists call a superionic state, where certain lighter elements move almost fluidly through a lattice of solid iron, a phase of matter that behaves like neither a true solid nor a true liquid. Other research has found signs that the inner core's structure may be changing over time, hinting at slow transformations happening at the absolute center of our planet, changes that could subtly influence Earth's magnetic field over long timescales. None of this is settled science. Some of it remains actively debated among specialists. But together, these findings paint a picture of a planetary interior that is far more dynamic, far stranger and far less understood than the simple diagrams and old textbooks ever suggested. Step back and look at everything together, and a pattern starts to emerge. Ancient tectonic plates sunken hundreds of millions of years ago, still shaping the flow of rock at the base of the mantle today. Continent-sized blobs of unusual material, possibly contaminated by leakage from the core itself, that may have determined whether this planet could ever support life. Earthquakes occurring in places earthquakes should not be able to occur, forcing scientists to reconsider what rock can and cannot do under extreme pressure. And at the very center, a core that may not be the simple solid sphere it was long assumed to be. None of these discoveries stand alone. Every one of them points toward the same unsettling conclusion. The deep Earth is not a static, finished structure sitting quietly beneath our feet. It is an active, evolving system, still shaped by processes that began billions of years ago and are, in some cases, still unfolding today. We have spent centuries mapping the surface of our planet in extraordinary detail, charting every mountain range, every ocean trench, every coastline. And yet the space between the crust and the core, a region making up the overwhelming majority of Earth's volume, remains one of the least understood frontiers left in modern science, more difficult to observe directly than the surface of Mars or the rings of Saturn. That comparison is not an exaggeration. Spacecraft have photographed the surface of Pluto 5 billion kilometers away. Robotic landers have drilled into the soil of Mars. Telescopes have captured the glowing ring of light around a black hole 55 million light-years from Earth. But no human instrument has ever traveled more than about 12 kilometers into our own planet, a shallow scratch compared to the roughly 6,400 kilometers separating the surface from the center. Everything scientists know about the deep Earth, the flowing rock of the D double prime layer, the sunken tectonic slabs, the mantle blobs beneath Africa and the Pacific, the earthquakes 90 kilometers down, the strange inner core, all of it has been inferred indirectly through the patient interpretation of vibrations traveling through solid rock. It is one of the most remarkable feats of deductive science in human history, reconstructing an entire hidden world using nothing but the echoes of distant earthquakes. And it means that everything we currently believe about the deep Earth remains, in a very real sense, an evolving hypothesis, subject to revision the moment better data arrives, exactly as it has been revised again and again over just the past 2 years. There's something quietly humbling in that. We tend to think of exploration as something that happens outward, toward other planets, other stars, the edges of the observable universe. But some of the strangest, most consequential discoveries of the past decade have come from looking straight down into a world less than 1/10,000th as far away as the moon, yet still barely explored. If the emerging picture from Rutgers and Princeton holds up under further scrutiny, then the very existence of life on this planet may trace back to an ancient chemical exchange between a molten core and a cooling mantle, an event that took place before there were oceans, before there was an atmosphere, before there was anything alive to witness it. Under that reading, the difference between a living world and a dead one might not come down only to distance from a star or the presence of liquid water, but to something far stranger, unfolding in total darkness, nearly 3,000 kilometers beneath the surface in the earliest, most violent moments of a planet's birth. Scientists still do not know for certain. The hypothesis is compelling, grounded in real seismic data and careful modeling, but it is not yet proof, and researchers continue to test it against competing explanations. What is certain is this: the ground beneath your feet is not the solid, finished, unchanging foundation it appears to be. It is a living system in the geological sense, still moving, still shifting, still capable of surprising the scientists who have spent entire careers trying to understand it. Every few years, new instruments and new methods peel back another layer of that mystery, and every time they do, the picture that emerges is stranger and more dynamic than the one before it. Ancient plates still drifting through the mantle after hundreds of millions of years, solid rock flowing like a river nearly 3,000 kilometers down. continent-sized structures that may explain why this planet, alone among the rocky worlds of our solar system, became capable of supporting life. An inner core that may not be the simple, solid sphere generations of scientists assumed it to be. We built spacecraft to look outward across billions of light years, and in doing so, we finally found the tools sensitive enough to look inward into a world hidden directly beneath us the entire time. The next major discovery about our own planet may not come from another mission to Mars. Or consider what it would mean if the core leakage hypothesis is eventually confirmed beyond reasonable doubt. It would mean that the difference between a living planet and a dead one was decided not at the surface, where oceans formed and continents drifted, but in total darkness, in the earliest few hundred million years after Earth's formation, when a molten core exchanged trace. Elements with an overlying magma ocean in a process no telescope will ever observe and no spacecraft will ever witness firsthand. It would mean the habitability of this planet was, in some sense, written into its geology before there was a surface stable enough to call an ocean, before there was an atmosphere thick enough to call sky. And it would mean that somewhere out among the thousands of rocky exoplanets astronomers have already cataloged, the presence or absence of that same kind of deep, ancient core mantle exchange might be one of the hidden variables separating a world that could one day host life from one that never had a chance. A variable no current telescope is capable of measuring directly, hidden beneath layers of rock and pressure that light itself cannot penetrate. That is the strange position modern geoscience finds itself in. We can photograph a black hole 55 million light years away with enough precision to trace the base of the jet erupting from its edge. We can capture light that left a distant galaxy billions of years before the Earth even existed. And yet the middle of our own planet, less than 6,400 kilometers beneath the chair you might be sitting in right now, remains something we can only reconstruct indirectly. One earthquake, one seismic anomaly, one laboratory experiment at a time. Every one of the discoveries in this story, the flowing rock, nearly 3,000 kilometers down, the sunken tectonic plates still shaping the mantle after hundreds of millions of years, the continent-sized blobs that may explain why this planet became capable of life, the earthquake that broke the rules and waited half a century to be believed, arrived within the last 2 years alone. If the pace of discovery keeps accelerating the way it has, then whatever we believe about the deep Earth today is almost certainly incomplete. A snapshot of understanding destined to be revised again and again as researchers keep listening more closely to the ground beneath us all.